Women Who Code Python event. Our mission, we're a global not-for-profit dedicated to inspiring women to excel in technology careers with emphasis on excel. We don't just want you in the door, we want you leading. We have 4 goals. We want to empower women with the skills needed for professional achievement, educate companies out there to better promote, retain, and hire us talented women, build a global community where networking and mentorship is valued, and develop role models and support this generation of engineers. We do have a code of conduct. We are an inclusive community. We want an empowering experience for everyone who participates and supports our community, and that is regardless of any of the classes that you see there, up to and including your preferred programming language. Although you're going to get really sick about hearing about Python, because we do love our Python here, but we certainly aren't going to chase you away if you want to discuss something else. Our events are intended to inspire women to excel in technology careers, and anyone who is there for this purpose is more than welcome, and we do not tolerate harassment. Our code of conduct applies to all of our events and our online communities, and you can read the complete code of conduct there at that URL below. There is also a form for reporting any violations or concerns that you have. We have 6 of these online track communities currently: front-end, blockchain, this one, Python, mobile, cloud, and data science. Oh, and we want to thank our sponsors. And the reason I said a little oh is I thought this was further down in the presentation, but here it is. This would not be possible without these fabulous sponsors: McKinsey, Python Foundation, the Home Depot, and Atlassian. And this is ML Mondays. And this is the 13th of January, not 2019 though, 2020. I guess I hopped back in my time machine when I was making this slide. No more day drinking for me. This is Maths for ML Part 3. It's a study group hosted by Yashika, Bethany, and the lovely Liliana, who I should have also put on this slide, so apologies.
I am here just for support.
She is here for moral support and to point and laugh when we make mistakes. So what is this study group thing? And all of you can kind of tune out if you've been here before, but if you haven't, this is a little bit different from webinars. We want this to be semi-regular and ongoing. So we're pacing ourselves. We're taking our time with the topic, and we expect it to be fun, and we want to increase our knowledge together. So none of your questions are stupid or silly. We are all here to learn, and we'll take as much time as we need. We also would love this to be collaborative. I want to learn from you. I hope you want to learn from each other. And so we encourage asking questions and doing collaborative work. So this is not where you listen to a presentation from an expert, because everyone here is learning. Also, we're not going to be creating notes or really slideshows for this study group, but we are recording this session, and we do provide a repo for community notes and code, as you can see. We have some notebooks there, and we paste resources there, and hopefully eventually we'll be working on projects there together. This is just a quick review of what exactly is ML to orient us. So ML is machine learning, so it's an application of artificial intelligence. And it provides a system the ability to automatically learn and improve from experience. And experience here means data input. And this is without being explicitly programmed, although depending on the type of ML you're doing and depending on the method that you use, there might be more or less explicit programming. So it's taking what we have, which is data, and going to what we want to know, which is predictions from new or unseen data. In ML, a model takes patterns from the data provided and learns from that data. So the more we teach the model, the more data and patterns we feed it, the better it can predict the outcome in the data that it has not encountered before. But the model's only as good as the data and patterns it's fed, and that's something we'll be revisiting. And this is just from the last time, it's computer math for ML. So a lot of ML and AI can look pretty scary because it's a wall of Greek characters. And even when you understand that sort of stuff, it can kind of be tough to plug through that. but Python can do the math for you. That's what this is all about, is being lazy in the best possible way. So once you orient yourself with the core ML concepts, you can let the scientific Python stack of libraries do the heavy lifting for you. And with that, I believe that that's all the intro slides that we have. And so I think I'm going to hand this over to the lovely Yashika, and she can get us started on the notebook that we put together for this session, which is a continuation of letting the computer do some of the ML math for you. And Yashika, if you might be muted.
Can you see my screen?
Yes, I can see your screen great. How's everybody else doing with this screen? We've got a chat here. Awesome. Okay, looks like everybody can see your screen fine, Yashika, if you want to start in. Or I can do the intro, either way.
Yeah, go ahead.
Oh, you okay? I'll go ahead then. Well, you've got the share on though, so do you want to stop sharing and I can share my screen, or?
Work either way.
I'm sorry, what?
Works either way.
Yeah, she said that works either way, so you can start and
you know what? Go ahead. She could go ahead. You go ahead.
Okay, so previously at the MS study group, we started with NumPy and Matplotlib, and we covered some of the functions. So we are just carrying forward NumPy here, and we are going to just introduce some more functions in NumPy. So first of all, when we by referring it, first reason is vectorization is a process of converting a matrix into a column vector. So when
Yashika, it seems like your audio is cutting off right now. We can't hear you very well. Yashika, can you hear me?
hello.
Yeah, we couldn't hear anything that you were saying. You were cutting off.
Okay, so I should start again.
Yeah, let's start again and see. Yeah, because it was cutting off your voice.
Okay, so previously we did some functions in NumPy. We covered some functions, and now we are just carrying forward and just introducing some more functions in NumPy. But before that, we are going to tell you the reasons why NumPy is important and preferred over other libraries and lists. Because we also have lists in Python that can do almost similar stuff that NumPy does. But we are using NumPy here because when we create lists, the first reason is vectorization. So when we create list and we want each element of the list to be multiplied by 2, and if you do, let's say you have created a list li and you want all the elements in the list to be multiplied by 2. So you do li multiplied by 2, but it doesn't work that way. It won't multiply each element by 2, rather than it would just print out the list 2 times. So that is not the case with NumPy. If you want a certain operation to be applied on each and every element of a NumPy array, you can do it easily, and that process is just called vectorization. So because of that, we prefer NumPy over lists. And it also significantly decreases our running time. because most of the operations in machine learning and deep learning are complex matrix calculations. So using NumPy, you can save a lot of running time, and the complexity is also decreased because of that. And the second point why we use NumPy over lists and other libraries is the random number generation. So last time we saw some random functions like randan and randint, and that is the reason why we prefer NumPy over lists, because we can randomly generate a lot of numbers that could be useful for us, and we can even generate multidimensional matrices. We last time generated 3D matrices also, and we can also generate matrices more than 3 dimensional. Like we can generate matrices of dimensions 5, 3 or 6, 4, any dimension you would like to create arrays of. And you know already that multidimensional matrices are called tensors. If the dimension is greater than 2, then it's called tensors. And yeah, we already saw last time that creating 3D dimensional matrices manually is very tedious. So with NumPy, we can just give the dimensions and we can get the random number matrices easily. So that is the reason that we can get clean data instead of tedious operations. The third point is broadcasting. So NumPy can handle arrays of different shapes during arithmetic operations by expanding a smaller matrix to fit the shape of a larger one. So for matrix operation, as you know, the inner dimensions of two matrices should be matched. So that can be easily handled using NumPy, and the process is called broadcasting. And there's also a function called transpose in NumPy, with the help of which you can transpose the matrix in case the dimensions of the matrices are not matching and you are not able to multiply two matrices. In that case, you can take the help from broadcasting and then easily perform your multiplication operations. Okay, then coming to the fourth point. The fourth point is Fourier transforms and linear algebra optimizations. So there are a lot of functions and formulas that can be directly applied using the NumPy functions. If any of you have seen Fourier transform formulas or functions, they are quite much complex, and it's very tedious task to manually perform those operations. But with the help of NumPy, you can easily perform these operations. And obviously, we need to optimize our algorithms in machine learning. So that could be done with the help of NumPy. We just simply have to enter our parameters in the functions, and we can get the results easily instead of computing and performing a lot of operations using a lot of loops. You can save yourself from all that tedious work with using NumPy. So the last point is speedy computation. So as I already told you, lists take a lot of time to compute a certain operation, but NumPy is quite much faster than that, and all the complex matrix multiplication operations and all the matrix manipulation operations can be easily done and fastly done using NumPy. So that is the reason. That is the most important reason that we prefer NumPy. Because when we work in deep learning, there are most of the algorithms that takes a lot of time. So in that case also, NumPy helps our task by computing the functions and matrices faster and easier. So yeah, these reasons are enough for us to prefer NumPy over any other thing. Bethany, do you want to go over these functions?
I think I will. I mean, sure. We can just take a look at this. So this is just a quick review of what we need to kind of install. So these things, if you were to do them on your computer, you would need to install the NumPy library, and you would need to install Matplotlib. And most commonly, you'd call pip, which is the Python package manager, to install those for you and to install the dependencies. And here they're doing an exclamation point because if you were running this notebook on your machine as opposed to in the cloud, this would allow you to check to see if they were installed without having to go to the command line. And then the next thing down there is how to, once you've installed them, import those libraries. And there's a couple conventions in the Python world for doing these so that you don't have to type everything out and risk a typo, which I'm infamous for. So you import NumPy as NP, and you import matplotlib.pyplot, because no one wants to type that, as PLT. And once you have that, then you are good to go with our examples. And since Yashika's running this in Collaboratory, it's a good bet that they're installed, but we're going to do it anyway for the sake of example. And because it's really fun, we're actually going to do some 3D plots, which is what the MLP toolkits import is about. We're waiting for the chubby gophers in Google Land to get their act together and install stuff. All right. Did you run the import cell, Yashika?
Yeah.
Okay, cool. I'm just double checking. I sometimes forget to run the import cell, and then I wonder why my stuff isn't working. All right, so we're going to warm up with a few drawings. So we're going to practice the concept of array and matrix a little more with the help of Matplotlib. Matplotlib is the now a little bit old and moldy, but still awesome Python library that plots graphs and figures. And there's a link to notes where we introduced Matplotlib in the previous session. We're going to create a 3D plot with a matrix, and we're going to randomly generate those numbers because we're lazy in the best sort of way. So we're going to use np.random.randint to create a three-dimensional matrix. So if we go ahead and run this. Oh, actually, I guess we should go through the full example. And a three-dimensional matrix is one that has rows, columns, and then a third dimension. I think you need a third, don't you need a third? Yeah, you need a third dimension there, right?
Okay.
What?
So
The data type ellipsis? Oh, is that the, yeah, the dot, is it not liking your dot, dot, dot on line 5?
do you want to share your screen for this part?
No, 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 I'm saying on, in the cell that, I'm sorry, go ahead. I think what it's having a problem with is that what you want to find the data type of is the multi-D random, right? You don't want to find the data type of the ellipsis. You want to find the data type of the variable, I think is what this means here. Yeah. And then we need to call dimension on it. Yeah. So Karen has a, let's see.
Yeah, she wrote li instead of random. So that was the error.
Yep. There you go.
Yeah.
And so if you make it a little bit, if you make the data size a little bit bigger, like 333, it might pop up a little bit bigger. There we go. So one of the reasons why we say that Matplotlib and these libraries are a little bit old and moldy is that it does take a little finagling to make your visualizations like super slick. And by default, sometimes they can act a little bit funky in these notebooks. That being said, I think it's super cool that that's all it takes to make a 3D plot. Like, that's not very much code. That's pretty cool. Yeah. Does anybody want to suggest a bigger sample size or a different size overall to plot? We can play with this a little if we want, or change colors or change markers. There's all sorts of things you can do. Okay. I guess not. I mean, we could double or triple the size. You want to do a 999 instead of a 333? And then maybe change the sample, the random points to, oh, is that not? Uh-oh.
Too many values to unpack.
Yeah. Maybe that's too much or too big.
Too many values to unpack again.
Yeah. Well, 333 is it then.
So, okay, at least I changed the color to blue.
I like the blue. So Emily Davis is asking, Ashika, perhaps you could tell her what is changing when we are changing the size, that size parameter there.
Okay, so when we are changing the size, that is changing the size of the array to be created. Multi-D random here is an array. More specifically, it's a tensor. So when we change the size, we are changing the number of elements present in the tensor. So 3, 3, 3 signifies that there are 3 rows, 3 columns, and the depth is 3. So when I change it to 6, 6, 6, that means we have 6 rows, 6 columns, and the depth is 6. So this is just telling the number of elements present in our tensor.
Yeah. And for whatever reason, when we go to 9 by 9 by 9, it makes whatever's going on unhappy. And I don't know if that's because of our random sample size or some other problem there, but there's some sort of render problem when we get up into higher than 3 layers. But yeah, that's what and you can see that down there where it says the shape is 3, 3, 3. So that's 3 rows by 3 columns by 3 layers.
Shall we go to the next part?
Sure. Let's do that. So these are some more handy features because, you know, as you've seen from previous examples and previous sessions, these tensors, these matrices, these arrays come in different shapes and sizes, and it's hard to hand edit these without making a mistake. So this library gives you a bunch of really handy methods like reshape, partition, and concatenate, which you can kind of guess at what they do by their words. And so that's what this little next section is about. So NumPy Reshape helps you reshape an array or a matrix. So here we've got an array. We're doing an array of random integers. And then we go down and we take what was once a one-dimensional flat list-like structure, and we call reshape on it, and then we hand it a dimension. And the dimension we're handing it is 5 rows by 2 columns. So if you look, you see the first array, one flat line, and then the reshaped array, which now has 2 columns. And so reshape is very handy for like generating, say, a list of 1,000 numbers and then saying, no, what I really wanted was, you know, a cube or something else. And it will more or less do the right thing. Although, you know, if you end up with a ragged array, like, you know, one too many, it's not evenly divisible, then that can be a thing. But yeah, it's very handy. So partition takes items and separates them, as you would guess. It does a sort first, and then after the sort, it'll sort the values based on the index value. So. Shika, do you want to explain what's going on here?
Okay, so we just created a random array using random and giving the size 1,9. So here you can see 1 row and 9 columns. And then we can do the partition on our array that is named here as list underscore A. And then we can mention the value that how do we want to sort the list, on what behalf, on basis of what index value. So here kth signifies the index value, and here's its true. And then we are printing our original array, that is list underscore A, and then we are printing our array with partition, that is list underscore part. So here you can see this is our original array, and here is our array with partition.
Perfect. And then this next part we have is a sample of concatenate, and that's where you glue 2 things together. So this one, we just have a quick example of an array A and its size, and an array B and its size. And then you can concatenate the 2 together. And I believe, if I'm remembering correctly, Ashika, concatenate requires that at least one dimension match, correct? You have to be able to glue it together at least along one dimension.
Yeah.
Yeah. So if they're completely disparate, then you're going to have to do other things, because you can't glue 2 things of entirely different shape together. So yeah.
So then that is the case when reshape comes to your rescue. Then you use reshape to make the dimensions match and then perform the operation. Yeah.
Yeah. So oftentimes you'll find yourself revisiting reshape over and over again until you can kind of reshape it in a fashion that will fit into the jigsaw puzzle, which is why this is so handy. If you imagine trying to hand edit this or hand specify that, you'd go insane quite quickly, I think. So yeah, and that's the review of matrices. And we've got that fabulous Neo in the Matrix sort of image there. So this is just a little blurb on how matrices and machine learning are really related. So these are some of the most, I know we sound like we're repeating ourselves over and over and over again, and in a way we are, but matrices and tensors are one of the most fundamental and important elements for calculation in science and mathematics, because they turn a vectorized representation into 2-dimension or 3-dimension or n-dimension tables that humans can kind of grasp. And that's a whole lot simpler to read and a whole lot simpler to interact with. But it's more than that. It's more than just holding or looking at the data. They also encode the valid actions you can take on the data representation, which is kind of an interesting thing. So matrix multiplication is one of those things, right? You don't have to like know the underlying kind of calculus of the situation. You just, the matrix itself encodes what you can do, right? You can't multiply a matrix unless the inner dimensions match. And if they don't match, it's not doable. And you don't really need to know anything else but that. And there are other operations that matrices encode in the same way, which is a very nice thing. It's a very nice representation. And those scary Greek symbols, you know, the matrices are a shorthand for representing a lot of that sort of thing. And it's also in a format that can be better processed by CPUs and GPUs in our computers. We're still doing things like partial derivatives, but they're being represented in a space that doesn't require, it's a different notation. So there's some Medium Post links here, 2 different ones that that kind of talk about this and talk about how major machine learning, like mathematical formulas, are encoded and represented in matrices. So that's just kind of a pitch for this. Linear algebra can feel really weird because of this kind of shift to a different dimension or a different plane of calculation, but it's all for the good. All right, so I think with that kind of covers our whole kind of matrix review, and we could kind of have a little discussion there, or we can jump from there straight into kind of an overview of what we're going to go into in depth next session, which is our very first machine learning kind of algorithm, which is, well, it's not one algorithm, it's a whole topic or collection, which is linear regression. So.
Does anyone has any questions about what we just reviewed?
And you can pop it in chat too. You don't have to speak up, but we also love people who chat. I mean, talk. All right, we can go ahead and continue. And Yashika, I don't know if you want to talk a little bit about the category of machine learning that this falls under, but also regression in general, and then, right, we'll lead into linear regression. But, or I can talk about this. So linear regression and regression analysis falls under supervised learning. So if you remember from a couple sessions ago, there's supervised and there's unsupervised learning. And supervised learning is where you have your input data labeled and your training and testing sets labeled as well. So you're supervising the machine in the sense that you have determined an appropriate outcome. So you have examples of what input data maps to what desired outcomes that the machine can learn from. And that distinguishes it from unsupervised learning, where you might not have those labels, but you are still expecting the machine to learn something by doing a grouping, a clustering, or other sorts of analysis on your unlabeled data set. But for linear regression, you have a supervised learning. And so the input features are known, or the input is known as features, and then the output are targets. And so we have an input table or matrix, and we have target or output matrices. And so whatever our model learns from the training is then used to predict the labels on previously unlabeled data, right? So we go through this thing where we know what the inputs are, we know what we expect the outputs to be, we do cycles of training on that, and then as the final test of our model, we give it unlabeled data to see if it has now learned the relationship between the input data and the expected output. So that's kind of the general sort of thing. And so we have regression and we have classification. And those are kind of the two general areas. And with regression, you can have univariate linear regression. You can have multivariate, which is where you have multiple inputs as opposed to just one. And that breaks down further from there. But for now, we are just going to focus on regression. Do you want to do that piece, Yashika?
Okay. So I hope regression is clear to all of you. Do you have any questions you can ask in the chat? Because then only we can move on to linear regression.
Okay.
No?
Yeah. So do you want to explain a little bit about regression in general?
Yeah, I can. Okay. So as Bethany told us that regression is a type of supervised learning algorithm, and in supervised learning algorithm, we know that what is the input and how the output would look like corresponding to that input. So basically, we have both input features and corresponding target labels. And target labels are nothing but output corresponding to each of the input features we have. So based on that, we have our first category in supervised learning, that is regression. So regression is an algorithm in which when we train our model on the basis of the input features and the corresponding output to that features, we get a generalized idea that, like, we just first of all train our algorithm, train our model on basis of the data we have. We tell it what the correct answer would look like. So if we have some features, we are gonna tell that what these features will lead to us, that what output will these features give to us. And then on the basis of that, our model generalizes the idea, and then we give it some unseen data. In that case, we just give it the input and we expect it to tell us that what the correct answer would be. So in that case, our model uses the generalized learning that it has gained after the training, and then it just predicts the correct answer. So that is basically regression. And the difference between regression and classification is first of all, the similarity is both regression and classification are under supervised learning. So both of them require the input features as well as the target labels or the output. So when the model is trained and then when the testing comes, the difference is, in case of regression, you'll get an output that is continuous. So remember, we did a lot of stuff with continuous and discrete variables in our Maths for ML session number 1 and 2. So based on that, regression will predict the continuous valued response. So for example, let's say you have to predict the prices of the house. So you have number of bedrooms, you have the locality, you have the number of schools nearby your house, and based on all these features, you want to predict that what could be the price of that house. So first we train our model on the training data. So we show it a lot of correct answers. Like we input a lot of features, and then we tell that this is the output corresponding to these features. Then our model, after getting trained on all that data, generalizes the idea. So so whenever we give it new data, it is able to predict that what would be the cost of the house based on the features we input to it. So that is a continuous valued response. The As you can imagine, the price is continuous. So in that case, regression algorithm would predict a continuous valued response. Whereas if we talk about classification, in classification, the output we will get is the discrete values. So a very popular example is, let's say we want to classify if the cancer is malignant or benign. So in that case, first of all, we train our model based on the data. We show it data and we show it the correct answers as well. And after learning and getting trained on all of the data, when we show it unseen data, we don't give it the output, we just give it the feature and ask our model to tell that if the cancer is classified as malignant and benign. So in that case, we have only two classes. So we will get either malignant or benign, either of those. So in that case, since the output is discrete, so our algorithm is known as classification algorithm. So that's the basic difference between regression and classification. And
the way I like to visualize that too is when we talk about continuous versus discrete, and tell me if this is not helpful to you, but the way I think about regression, whether it be univariate or multivariate, if it's linear, what you are looking for is, in mathematical terms, is you are looking for the computer to learn the equation that goes with a line that describes the relationship between the features that you've put in and the outcomes, the range of outcomes that you could have. So again, if we go back to our example of housing prices, it is, you're trying to find an equation for a line that gets drawn when you say have a 3-bedroom house that is potentially worth X amount of dollars, right? So you're trying to see which of the features are kind of the driving force for this valuation line, but it's a line. It is a range or an area of probability. It's not an exact thing, right? It could fall anywhere in a range. And what you're doing is you're saying that there's a high probability that these features are associated with this area of the trend. So you're looking for an equation for that trend line. Whereas with classification, it's like that Bernoulli distribution. Is it or isn't it? Are you on this side of the line, or are you on that side of the line? And it's a line. And so it's a yes, no. Or maybe it's, a grid, but you're either in an area or you're not in an area, which makes it discrete, right? And so that is how I fix that in my head. Emily, though, and Yashika, maybe you can talk about this or not. Emily had a question about outliers and about where outliers make the biggest difference. Is it only in linear regression, or is all regression prone to being skewed by outlier data?
As far as I know, outliers can affect each and every algorithm, not just linear regression. It can affect other regression types also, because that is the outlier. So I assume that most of the people don't know what an outlier is.
Yeah. Yeah, I would, you know, say the same thing, is that because what you're looking at is a generalization, right? That's what that equation means, that the more outliers and the further the outlier is, the more that line has to be influenced by data that may be statistically right at the ends of the distribution. And so you can end up with some things that don't make a whole lot of sense, which is when you start looking at maybe other algorithms besides regression, although regression is a super handy algorithm. A lot of things can be solved using regression. Yeah, so there's regression, and then there's linear regression, and then there's different methods of doing linear regression. So the most basic and infamous of those is one we call the ordinary least squares, which is the next thing we're kind of going to go over. Yeah. So ordinary least squares is an interesting one. Again, if we're thinking about that mythical trend line, if you plot all of your data and then you try to find a line that best represents that data, ordinary least squares helps you adjust the tilt of that line and the position of that line by basically calculating the distance to that line from every single point in your data set, essentially. So you basically, you know, you do the calculation, and what you are looking for is a line that minimizes that distance for every point in your data set, which is a lot of math, which is why we're happy there's NumPy. And so basically you calculate the distance for every single point, and you sum them all up, and you see if that is the best you can do. And then you ask yourself, can I do better? And you keep going, and you draw the next potential line, and you calculate the distances again, and so on until you've minimized what we call the cost function, right? So you've minimized the distance of all of the points to the best of your ability so that you have this trend line drawn. So it's easier actually to plot this and to show than it is to talk. So that's what we have next, is we're going to plot one of these so you can kind of see what we're talking about.
So here I've just created a kind of data set, you can say. So this is how our original points look like. This is the x-axis and this is the y-axis. So we have 500 samples, and we have taken the number of features only one here. So this is what our data looks like. So we want to generalize a line. That line is nothing but a linear regression model. So we want to generalize a line as such. In case we input something new, like this is the data we have and we are going to train our model on behalf of this. But in case you input some point that maybe lies here or lies here, so in that case, I want my model to make predictions that what could be the correct answer. So in that case, I would like my model to generalize the idea that it should learn from this training on behalf of the data it has. So let me run the next cell. So that was our data initially. So this is something where we are using linear regression and fitting our model and all the stuff. We will go through all of this in the next session. But broadly speaking, so here is our data, and then we have just imported a linear regression model, and then we are fitting our regression regressor on the X train and Y train. So here, based on our data, we are training our regressor so that it could make the correct predictions. So when it got fit, we are going to see that how our model would look like. So here, the red points are the points or data that is scattered over this plot here, and the blue line you can see is the linear regression model that has learned all the features and relation between the features and the output, and based on the relation, it has generalized itself as a straight line here. So based on this straight line, this is what our model has predicted. So all the red lines that has all the red dots that are on the blue line are those predictions that our model has made correctly. So as you can see here, some red points are coincide by the line. So these are the correct predictions our model has made. But the red dots that are away from our line are the predictions that our model has missed. So the distance between these red points or red dots and our model, that is the blue line, is the error we have. So always we try to minimize this error, and that's where ordinary least squares come in the game. So in that case, we want to minimize the error. So the red dots is our actual values, and the blue line is our predicted values. So we always try to fit our model as such that most of the red dots fall on this blue line so that the correct predictions are made. Does that make sense?
Yeah, and the real challenge here, so you look at this and you say, well, this is an awful lot of fuss and an awful lot of math for a straight line. But you want a good generalizable model so that it can be successful in predicting from new data. If you start to fiddle with this so that it starts to get wavy and start to fit all of these points, you get into an area that we call overfitting. So you can force this into fitting your training data exactly, but what you lose then is the generality of the model. So it's expected that it's not going to be like 100% accurate, especially with a small sample size, which is why bigger data is better in these situations. But also, it's probably never going to be 100% accurate because you're kind of trying to walk the line here between a generalizable equation that works on a lot of data and one that has good predictive power, right? And you kind of have to balance those two.
So why would you want to force it?
Sometimes, if you retune your parameters or you retune things, you might get a little bit better fit, but you don't want to exactly fit your training data because the whole purpose of this is to make predictions on data you've never seen before. So you don't, you may want to tune it a little bit because you may feel that your data set has some particular features that that you need or that you want to adjust for, but yeah, you don't want to overdo it. So that's kind of the balance. The balance you fit. Like if you look at this data set and you look at the overall data set and you say, well, but there tends to be, as Emily asked earlier, there tends to be a lot of outliers in this data. Like maybe you do some tuning around that, right? Or some adjustment or some selection of parameters. So you may not always want just the happy path. But you don't want to go too far down that rabbit hole because just because you get your model to come back with 100% prediction on your training set doesn't mean that it's actually going to work on data it's never seen before. So that's kind of the art in the ML, is that sort of tension. And that's true of not just linear regression, that's true of just about every algorithm that is out there for machine learning, is that you have to kind of walk this line between like the data and the predictions you want to make and where you think the relationships are in the data and which ones are important. and you know, and fit that as best as possible, but it needs to be able to be general enough that when you feed it new information, it's not going to be overly biased by what you did to make it fit. So, yeah. Or overly biased, period, because of the data you're using. But that's a whole different story for a different session. I don't know if that makes sense or not, but.
Yeah, that makes sense. Thank you.
All right. So yeah, so one of the things that I find just interesting, really fascinating about this, and we didn't get a chance to put a visualization in here, but maybe I might be able to pull one up, actually. Let me see if I can do that really quick. It's really cool to watch an animation of an algorithm, a machine learning algorithm doing this sort of adjustment. And you can see it on successive cycles going through, let me see if I can find it here, going through the learning part of it. And the line will shift and shift and shift until that cost function is minimized. Let's see. Bear with me for a moment, or discuss among yourselves. I thought I had this open in a browser tab, and now I don't. Give me just a sec. Oh, it's way too silent. Somebody pipe up and fill the space, please. Okay. Yes, so here, let me share share my screen here really quick. This is a sample that is done in the R programming language. Let's see here. And it's a sample of least squares. And here you can see, it'll reset itself here in a second. On the left, you can see how subsequent rounds of it trying to find a regression line run. And on the right, what you can see here is a graph of the cost function here being, right, how far away from the line each of the points are. And you can see at some point, it hits a minimum right down here at the bottom, and then of course, shoots all the way off into the universe in the other direction. Of the way they do it. But here is kind of a visualization of what's going on here, where it is taking the data points and then trying line after line after line until those distances are minimized. And so what it really should be doing, what a algorithm that's not forced to be off path would be doing, is it would stop somewhere here in this area at what we'd call the optima. You know, ideally, if you've done your job right, it'll stop at the very, very bottom, right, at the very minimum, but somewhere in that area. But here it's being forced to kind of go off the other direction. All right. Well, I think that actually is all the material that we had to kind of go over for this session. And we have a few minutes left if we want to have a quick discussion, or if anyone has questions or anything else. Can I post the YouTube link for the recording? Yes, we can definitely do that. Let updated copy of the notebook be added to GitHub. Yes, we can definitely post an updated version of this to GitHub. You can go in and edit that so that you can access it, Dawn.
so if there is not any questions, I encourage you, everyone, next time you come with some questions so we can try to figure it out, the answers. If we know them, we'll answer them. If not, we can figure it out together. Because we want you to interact with us. So we just don't want to give you information all the time. We want information from you, even if it's questions, if it's things that you don't know or we don't know maybe.
Yeah, and actually it's really good for us as well because boy, I am by no means an expert on this topic, and it always helps if I work through stuff and people ask me questions, because it's a lot of stuff to keep in your head. It's a lot of math, it's a lot of concepts, and it can kind of feel like it really isn't, you know, until you start getting your hands in it, it can feel very disconnected from reality as well. So the matrix is still quite above your head. You know, matrix math, and if you'd like, I mean, that's the other thing. We do not have to march straight through onto linear regression and into the universe. And if matrix math or other things are confusing you, or if you want to do a whole practice session around those things, for me personally, I know doing a lot of matrix multiplication and addition and division, heaven forbid, helped me. For other people, that would make them crazy. So, you know, it just kind of depends on you and your learning style. But yeah, I would be completely down with either having a Slack session or having a Zoom session like this where we work together to solve a bunch of matrix and tensor, because it gets funky when there's more than 3 dimensions problems, if you'd like to do that. Don, what's the next topic? So the next topic is going to be going over various types of regression more in depth. So really going through least squares and things like that cost function, which, you know, trigger warning for scary math. On the other hand, you know, also celebrate because the power is yours, you know, to tell the computer to do the math for you. So we're going to go into kind of the math behind this regression and multivariate as well as univariate, right? So linear regression. And work with it more and work with some actual data sets. So there are some nice handy data sets that come with scikit-learn, which is one of the, you know, machine learning libraries. It's a starter machine learning library. So there's the infamous Titanic data set, which is, you know, basically all the passengers that bought, you know, all the various classes of tickets on the Titanic, and then who survived and who didn't. And it's a cool data set. And then there's also another data set that comes with Scikit called the diabetes data set, which is all like lifestyle information. And I don't know if that has blood sugar or not. I haven't looked too closely at the diabetes one. I know the Titanic one a little bit better. But it comes with those data sets. And so we thought we would do some regression on those data sets and kind of get our hands dirty with that.
Yeah, and also to mention that everyone is saying that exercises will be a great idea. Yeah, we have it in the idea, but it's always look at the concepts first, because you need to have a rough idea what the concepts are. After that, you can go and work in exercises, because those concepts will help you to develop the answers.
Yeah, and so that was kind of our intent this time. I know it feels a little bit lightweight, although those notes that Yishi could put in the channel are not lightweight, and we'll post some more resources too in advance of the next session. But yes, we are hoping to actually get our hands on specifically scikit-learn and running some things and doing that interactively in Zoom. I think it'll feel way better to actually see something happen in that sense and kind of push through that. So our goal is to try in the next week to get material for the next session up so that you have something to kind of work on for a week before we kind of all get together and work on the problems together. And so our next session, I believe, is going to be on the 27th. And it'll all be about linear regression, all about that and about the diabetes data set and the Titanic data set and maybe even a data set of our own.
So be on the look for in the chat. We'll probably publish that whenever we have the information for the exercises.
Yeah, so keep your eyes peeled. We'll put it in the ML study group channel in Slack, and we'll flag the various resources, and any of the resources that we want you to or think would be good for you to kind of review prior to the session. We'll post those in the GitHub repo as well, because I know sometimes Slack erases things, which is really not cool of Slack to do that. And so, yeah, the repo will also have links to specific resources.
That kind of reminds me that I posted a PDF last week or so about the, that was based on the notes from CS229 Stanford's course. So did anyone try that? Did anyone give it a read?
I think a few people did, but I'm not sure that we quite had our rhythm down for digesting it. So we may want to give it another read and come with questions next session, and we can repost that resource as well.
Yeah. And for the matrices part, if that is not clear, we can conduct a separate session for the matrices as well. Or if you have any questions, you can reach out to us on Slack or wherever you like to. But
yep.
Yeah, we can do that together. We can do that again also. But also you can give it a read from the internet and from our repos and from the previous notebooks, and then you can come up with your questions personally on Slack as well. You don't have to post that on the group, and you can ask us personally as well.
Yeah, our DMs are always open, and you can always ask in the Slack channel, and you can always too, if you don't like Yashika and I's explanation of something, we have a whole data science channel, so you can also ask questions in the data science track channel too, kind of wherever you like. Yeah, and you can also propose, like if you find what you think is a really good resource that helps you out, I would encourage you to, propose that in the, Slack channel, and there's some good exercises out there, and we can all benefit from, doing a little practice on this stuff. So, yeah. But thank you very much for attending. I would share the last half of the presentation, but you guys probably don't want to see more of those Women Who Code slides, although I can do that. Let me pull up the presentation.
I have a question slightly off the topic.
Sure, ask away, Dawn, please.
Yeah, you can unmute yourself if you want to talk.
Yep.
Okay, I guess I
please
can.
Do.
All right. Thank you. So earlier I was looking through the data science channel, and I saw a little mini boot camp that you did earlier back in the spring. And it was a conversation about this mini boot camp and 3 projects that you could use to start your portfolio. And I wanted to know if there's a way to get that material. I know it's after the fact, but was wondering.
Oh, I think that boot camp was from the data science Slack channel, but I could give you that information.
Yeah, okay. No, I mean, I think we definitely can. I think maybe one of the reasons why they have not posted that information is because I know that track is planning another mini boot camp.
Oh, okay.
And I don't know what the timeline is, and I don't want to commit them to any, and I don't want to commit them, but we have been in talks with the fellow for that track, and both of us have been saying we are going to help her. But what is happening right now is we're going through a process where the fellows on the tracks some fellows are leaving and new fellows are coming in, and they're going through a selection process for that. And so January is a little bit slow because they're doing that. And then once everything is changed over, I think in February, all of the tracks are going to get started cranking on like their content for the year.
Okay.
But I know that it's definitely in the pipeline that she is planning not only a data science boot camp with projects, but also an ML boot camp.
Oh, okay.
Yeah.
Yeah, but I believe that that one, she still have it from last year, and she's still sharing it. So I could ask, and I'll let you know. Yeah.
Okay.
I'll send a message, and if I have it, I'll share it to everyone so anyone can take a look at it.
All right.
Yeah.
Thank you.
Well, I'm going to do the usual. Thank you for attending, and please help us grow and get involved. You can sign up on the web page, but you can also message Liliana or Yashika or I directly in the channel here in Zoom, and we can add you directly into our Slack channel if you'd like to do that. Stephanie, we definitely want you as a volunteer, and thank you for letting us know that like the communication there is broken and we need to fix it. We'll get you signed up immediately. We've got plenty of work for people who want to do stuff, be a lead or an evangelist or anything else. And we would encourage you to join the conversation. And you can follow us on Instagram, on Twitter, join our Slack channel. That QR code will work and give you an invite link. And that final one is for the website. So thank you all so much for spending this Monday evening with us and listening to us blather. And I hope we see you next time.